Okay, good morning. We are going to look at vapor pressure diagrams, or vapor pressure, and there's a curve that goes along with it, also phase diagrams. And I'm going to split these up into two separate lessons and two separate recordings, really. But these first objectives go with the vapor pressure, and then the others go with the phase diagrams. If you watch this before break, if you want to do a test over break, please let me know by 4 p.m. tomorrow. I can send you the test. If we're back in the classroom on January 4th, like we're supposed to be, we're going to do equilibrium unit, which is kind of short and does not have a test. So there's going to be class time for you to get caught up if you're behind. All right, let's look at vapor pressure. So what is it? It's the pressure of a vapor above a liquid. So here's a scenario again where we've got liquid ethanol, and we're pretending like none of it has evaporated yet, and it's attached to this manometer. Remember, the manometer is this curved tube. It's got mercury in it. This is a vacuum right here, so that if there's any pressure exerted on this side of the mercury, it'll push up into there, and it won't have any forces pushing back on it because there's nothing there. It's empty. Okay, so that's our starting point. And then we're allowing some of that ethanol to evaporate. When it does, it's a gas, and so it's going to exert a pressure. It exerts a pressure on that mercury, pushes it down, and then you can take a ruler and measure this distance from here to here and report your pressure in millimeters of mercury. All right, so that's what vapor pressure is. As the temperature goes up, as you might suspect, the vapor pressure will go up, because as the temperature rises, whatever this liquid is, it can break the forces that are holding it together as the particles move around more, and more of them will be in the vapor phase. So as N goes up, the pressure goes up, N being the moles or amount of the particles. All right, and then we usually take these vapor pressures, and you can measure vapor pressure at different temperatures. And here's a graphical representation of how, as temperature rises, the vapor pressure increases. Okay, and so there's a few substances here, and we're seeing the vapor pressure at various temperatures. Now, in that Dalton's law lesson, there was one part at the end here where I said if you collect a gas over water, a chemical reaction happens and you trap the gas. And there was a video where I showed you how that worked. So you've got the gas and there's water in the container too. And some of that water will evaporate and you'll have a mixture of gases, and that's why Dalton's law works. Well, this happens so often in lab that people have collected the vapor pressure of water for all kinds of temperatures. They've even got these things to the tenths and the hundredths place. So if you need to be really precise about it, you can be. Well, this data right here is this data right here. This, I guess, in the Dalton's law, it was from 15 to 25 degrees. So we've just got this tiny little bit of the curve here from about 15 to 25 for water, and so it's really the same thing. This is a graphical version, and what you saw the other day was just a table version of that. Okay, so we're gonna, in this assignment, you're gonna be interpreting some of these, this vapor pressure, these curves here, these diagrams. Let's talk about boiling and then volatility. So boiling, what is it? Well, in an open system, the boiling occurs when the vapor pressure, so that's this pressure of the vapor above the liquid, is equal to the atmospheric pressure, and that's the pressure pushing down. So here we've got an open system, and the atmosphere, like we talked about, has some pressure because of the molecules being pulled down by gravity. So they're pushing down. If you heat this substance up, looks like it's water. If you heat that up, then you're going to get a little vapor bubble, and it's going to want to rise to the top and exert a pressure. And when that pressure of that vapor equals that pressure pushing down, then it starts to boil. And you might notice that boiling can happen all over the sample. When you start boiling something, there's those bubbles that are all over the place, and that's different from evaporation. Evaporation only occurs at the top, and that can happen at any temperature. You can evaporate water when it's cold. It just evaporates more easily when it's warm. And that's just water breaking its intermolecular forces. There's an intermolecular force from one water molecule to another. So it's breaking that force just by virtue of it's moving around. So that's evaporation, whereas boiling, you have to have the vapor pressure of this gas above this liquid with the same force pushing up as this atmosphere is pushing down. All right, so normal boiling point, that's the boiling point at standard pressure. Here's a bunch of standard pressures from earlier lessons. The very first lesson talked about standard pressure in various units, and that's usually marked on the diagram here. So in torr, standard pressure 760. So you're getting the boiling point for these substances. So there's water, 100 degrees Celsius, that's its boiling point. So there's the temperature, 100 degrees, and there's the pressure exerted down on the water, and that also has to be the pressure, the vapor pressure. So when water has a vapor pressure here at 760, that's when it boils at 100 degrees. So that's standard pressure. But you can change the boiling point of water by changing the pressure that's exerted on the water. So if you're at higher elevations where the pressure is not as great, then the water is going to boil at lower temperatures, say somewhere in there maybe. And in the assignment, I think I'm asking you questions about when does water boil on Mount Everest and that kind of thing. So the intermolecular forces are what holds the one molecule next to another molecule. So the stronger that force is, the higher the boiling point, which kind of makes sense because you have to break that bond in order to get the molecules to break apart and start boiling. So stronger the intermolecular force, the higher the boiling point. Here's a piece of a video I'd like to show you about boiling water with ice. And he's just kind of walking me through what he did. He's heating some water to boiling in this Erlenmeyer flask. So you're getting a hot vapor here. The vapor's water, and that's okay. Okay, then he's going to close it. So now you've got a closed system. And he's cooling it with ice there. That's sort of, that'll pull the cork in there a little, or the stopper in there. He's turning it over, puts it on the ring stand. Okay, so think about what's happening. You've got this closed system. So this is like this is like the atmospheric pressure. So that vapor right there has a pressure that's pushing down, and then there's will be a pressure that's pushing up from these molecules here when they want to go into the vapor phase, and they always do. Some of them always do. So they've got a pressure that they're pushing up, and then you've got this pressure pushing down. So this is like being in where the atmosphere is. And what happens next is he cools. When he cools this, he's lowering the pressure pushing down on that vapor there, or pushing down on the water. So the water can start boiling because the pressure above it is lower now. So it doesn't need as much, as high as a vapor pressure to push up. Anyway, so that's boiling water by, really by lowering the pressure above the liquid. All right, and how about volatility? This is a vocabulary word. A volatile substance means that it evaporates easily at low temperatures. So if it's evaporating easily, then there will be more of those molecules in the gas phase. The more of them there are, the higher the vapor pressure. So as N goes up, the pressure will go up. N and P are directly related. So let's relate that to intermolecular forces again. So as the intermolecular force goes up, as this is strong, as if you have a strong intermolecular force, and water does have strong intermolecular forces, then there won't be as many of those molecules in the gas phase. And so that won't be as volatile. So water is not very volatile, but something like ethyl alcohol is. So, you can take a temperature here, say 60 degrees, and water's going to have this lower vapor pressure than ethanol will have a higher vapor pressure because the forces are weaker. Or even over here, same thing at 20 degrees, and then you can bring this one in, diethyl ether, has the highest vapor pressure because it's got the weakest intermolecular forces. The forces aren't being held together, or the molecules are not being held together very strongly as a liquid, so more of them go up into the gas phase. All right, so let's just look at maybe a quick example. We've got a few minutes left. Say 40 degrees Celsius right here. What pressure will ethanol boil? So you can look, here's 40 degrees and there's ethanol. So you bring that back over and it's going to have a vapor pressure of less than 200. So this is going up by hundreds, really, 100, 200. So I don't know, 100, maybe 130 or something. That's going to be the vapor pressure at that temperature. And so if the atmospheric pressure is the same, then that's where it would boil. Okay, so that's vapor pressure diagrams. And this is the practice that goes with it. So you're just I've got the same exact curves, so you'd be familiar with it. And then you're just answering these questions. Okay. So I will stop the recording here, and then I'll do the phase diagram lesson.